Welcome back. I'm Lisa Blackburn. This is my YouTube channel for everything I want to talk about science and math. And today we are talking about the gas laws in AP Chemistry. I have a video that's had over 26,000 views.
Congratulations.
Thank you. I still make no money, but you know,
Soon.
maybe one day. All right, so we're talking about the gas laws. This needs to scroll up. Whoop. Okay, so our warm-up today, I forgot to show you all the screen. For our warm-up, your test is going to be not Monday, of course, but the next Monday. So we're going to work on this for a week. We're going to be learning about gas laws and intermolecular forces, really in liquids. So we're going to talk about gases and liquids. So what is a gas? They can expand to do what? Y'all memorize this before. I think someone said it. They can expand to, she's saying it. They can expand to fill their container. You remember that now? Didn't you learn that in elementary school? Yep. When you learned what a gas was? They are highly what?
Energized.
They are. That would be a good one. But they're very squishable. They're compressible. They are highly compressible. And if you put them together, they make homogeneous mixtures. They don't make layers usually. They make homogeneous mixtures with other gases. So these properties of gases can be explained by the fact that gas particles are relatively far apart from each other. Okay, that's section 10.1. Can we scroll on up? Okay. 10.2, pressure. So the definition of pressure that you learned in physics class is pressure equals what?
Volume.
It's force over area. Remember that from physics class? When I teach physics, I always talk about how that this formula that the bigger the area, the more spread out that pressure is. So it actually is better if an elephant steps on your foot, because they have very big feet and it really spreads their weight out, than if a person is wearing stiletto heels and if they put all their weight on one heel on your foot, it'll go through your foot. But an elephant, you just like have to get him to get off. You're not even going to get a broken bone. I used to have a friend who I used to teach with at Pebblebrook, and she had two jobs. Her other job, she worked at Zoo Atlanta with the elephants, and she said that they would step on her feet on purpose because they thought it was funny, and like she'd be trying to get them off, and they'd just stand there. And she says, if an elephant's standing on your foot, you just wait till he wants to move. There's nothing you can do to make him move till he decides it's not funny anymore, and he'll let you go. Okay, so one of the big things that's important in chemistry that we talk about is atmospheric pressure. So this is how much the atmosphere, all the gases in the atmosphere are pushing down on you right now. And so it's defined as the force exerted by the atmosphere on a given surface area. So in the 17th century, many scientists and philosophers believed that the atmosphere had no weight, because you don't feel it, do you? You can't feel any weight. You've grown up your whole life under it, and it's just normal to you. But it's really tremendous. If you look at 1 square inch on your palm, the amount of pressure that the atmosphere is pushing on it is 14.7 pounds. 14.7 pounds. In an area that's bigger, as big as a foot, like your stomach, is 2,000 pounds. Right now, you are under tremendous pressure, but you've just lived under it your whole life, and you're used to it, so you can't feel it. But anyway, Evangelista Torricelli was able to prove that air does, in fact, have weight when he invented the barometer. Which is illustrated down here. So I actually have a couple of illustrations on this. I'm going to scroll up, if that's okay, so you can see the illustrations. His first one he invented was sort of like this. It was a bowl that had mercury in it that was open to the air. And as the atmosphere would push on it, that this is closed, it would squish that air and the mercury would go up higher in the tube. If there was less atmospheric pressure, then that air would expand and there'd be more air, less mercury in that tube. So he was able to show it that way. So, and also, after they invented the barometer, they started noticing weather patterns. So do you know what the barometer, like say if the barometer is high, does that mean the air pressure is high? Are we going to have storms or good weather? This is how you remember it. The highs, they bring clear skies. So if there's a low, that's when it's going to be a storm. The highs, they bring clear skies. Now you can remember that forever. So if you hear it on the news that a low pressure is moving in, no, there will be storms. Okay, back to what we're talking about. So there are a wide variety of units that can be used for pressure, about 7. The reason why is gases was one of the first things when chemistry was discovered that they really looked at closely. That was the first thing they studied was gases. And so there were scientists all over the world discovering stuff and making up their own units. So there's about 7. But in AP Chemistry, wonderful, they keep it to 3. So this is even less than when you were in honors chem. I made you learn more than that. And this is the ones you need to know. That 1 atmosphere, does anybody remember how many millimeters of mercury an atmosphere is?
720.
Close. You remember the 7, 760. Ah, that's familiar, isn't it? And the great thing is that's the same number, just a different ending for torr. It's still 760 torr. So here's the diagram, and here's some gas in a flask that's sealed with some mercury open to the atmosphere. So if the atmosphere has higher pressure, it's going to squish it. The mercury will go, this gas will get squished by the mercury coming toward it. And the difference in these 2 columns of mercury, that height will change. Can you follow that? Can see that? Okay. So in the ideal pressure, the gases in the sealed is this gas in that sealed flask higher. So out here, our pressure, according to this, is 764.7 torr. By looking at this, do you think this pressure is higher or lower than 764 torr? Higher, because do you see how it's squishing it more this way? It's like a little tug of war, and atmosphere is losing. The mercury's coming toward atmosphere. This is a higher pressure. Good job being able to figure out what's going on in that flask. So the mercury level, and how we know this is the mercury level is lower on the flask side. So it's been able to push it down lower. Okay, feeling good about this? Not too bad? Based on the information above, okay, determine the pressure of the gas in the sealed flask. So if we look at that sealed flask, the atmosphere was 764.7. Okay, but if we look back at this, we have the difference between these two, the difference between that level and this level, and we can subtract, and we get 32.6. Millimeters. Everybody see where I subtracted those 2 numbers to get the difference there? Okay. So now, if I was trying to get the total pressure inside the flask, I need to add that to the atmospheric pressure. And that equals 797.3. I kept trying to write that backwards. I was struggling with my dyslexia, 3rd period. Wanted to flip it upside down. Anybody else in here a little dyslexic? Your N's end up being U's, lowercase u's? Mine was, that was happening to me yesterday. I was trying to write fast. Every N was getting flipped upside down. All right. Based on the information, okay, so now we've got how much it is if we add it together. 797.3 torr. But if we wanted to change that to atmosphere, it's just a regular little dimensional analysis problem. So when we do dimensional analysis, we start with what we know, which is 797.3 torr. What do we write in the denominator?
76.
Right, 760 torr equals how many atmospheres? 1. Multiply what's on top, divide what's on bottom, and you get 1.049 atmospheres. That's not bad math. Remember doing math like this when you did gas laws and honors? I made you convert some torrs and some millimeters or mercuries and stuff. Okay, if you were to take this barometer up to the top of a mountain, would the difference in the height remain the same, decrease, or increase? Okay, think about, well, let's look at this. Let's back it up and think about it. Less pressure is going to be pushing on it. So what's going to happen to our mercury? It's going to go up that way, right? Okay, so this is going down, that's going up, so this is going to increase, yes. Very good. It's going to increase because of the less atmospheric pressure on the mountain. Okay, now do you remember the gas laws? Boyle's, Charles, Guy-Lussac, ideal combined. Time to remember them. Do you remember the song I sang you about them? The gas laws are good to know. You can use them everywhere you go. We're talking PV equals nRT. We're talking heavy duty chemistry. All right. Always got to sing the gas law song whenever you can, because there's not really that many opportunities in life to sing the gas law song. Okay, I didn't make up the gas law song. There's another guy who writes these songs. Okay, the gas laws. The first one we're going to talk about is Boyle's. So it's P1V1 equals P2V2. Robert Boyle discovered that when the pressure on a fixed sample of gas is doubled at constant temperature, what happens to the volume? Okay, so if I've got a balloon and I push on it, is the volume going to get bigger or smaller? Smaller. And in fact, it ends up 1/2 of its original value. So when pressure goes up, volume goes down. Is this a direct or inverse relationship? Inverse. So remember in math, if everything is in numerator land, nobody in denominator land, but you have more than one variable on each side, it's going to be an inverse relationship. And the reason why is to get one of these variables by itself, I have to divide, right? And to remember in algebra class when you learned direct and inverse, you were learning about y equals 1 over x. You can sort of remember, so you can see how it fits into your math class. Okay, so here we've got a problem, a Boyle's Law problem, and we're supposed to first look at our data and our graph and fill out pressure and volume relationship. We're going to start, if the pressure is 2 atmospheres, according to our graph, what is the volume? Yes. If it's 2 atmospheres, our volume is 50 milliliters. Everybody understand how I got that off the graph? Okay. Now what about the other dot? My other dot is 4 atmospheres. What's my volume? 25. So we got that from the graph, but now we're going to use Boyle's Law. And so Boyle's Law says if you take your first pressure and your first volume and multiply them, then if you've got one of the other two, you can solve for it. So on one side, I've got 2 times 50. What's 2 times 50? 100. And on this side, I have 10. I have to divide by 10 to get my volume by itself. What's 100 divided by 10? 10. So at 10, my dot is 10. So let's try this one. What about 15? On this side I've got 100, on that side I've got 15. Anybody know about how many times 15 goes into 100? 6. About 6 is 6.7. Okay, and now so we can graph that too. So at 15 it is 6.7, about right there. And now I can connect my dots, and it is the classic inverse relationship graph that you learned in math. Remember that graph? That y equals 1 over x graph from math? From Algebra 2? Mm-hmm. Okay, we're feeling good about these gas laws now? Starting to like them better? Maybe I need to sing the song again so we can all feel positive about the gas laws. Okay, the next one is Charles. Charles. V1 over T1 equals V2 over T2. Discovered the fact that when the volume of a fixed sample of gas at constant pressure will increase when the temperature of the gas is increased. So this is your hot air balloon. You heat up the gas and the volume increases, fluffing out your hot air balloon, right? And also then the density decreases. And the molecules spread out and the balloon flies. Anybody ever done it? Anybody ever floated in a hot air balloon? I used to want to. I thought it'd be great. But then you just see all these people who get caught in the power lines and die. And I think that is a horrible way to die. You see the power lines coming, there's nothing you can do to steer, you realize you are about to die. So I don't know. I'm not sure about it anymore. Maybe if it was tethered, you just go up and come back down. But I don't think I want to be on a free floating balloon. All right, let's focus back again. Using a ruler or straight edge, extrapolate the data in the graph below by drawing a line that passes through the data parts and intersects with X. What does extrapolate mean? Y'all remember that from algebra? It means to draw a graph connecting the points of what you know, but you don't stop there. You go on the graph paper, continuing the trend to the area you don't know, okay? So that's what we're going to do. We're just going to keep drawing straight on down. Now, so you got to watch out for extrapolation. It sounds right, it sounds fancy, but sometimes it's wrong. Imagine if my graph was number of Blockbuster video stores in the U.S., and it's going up, 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 and that's the data I have, and then I extrapolate it all the way to 2024, that I should buy some Blockbuster stock. Is that true? No, they're all closed, aren't they? So, watch out for extrapolation. That means they're making stuff up based on the trend, which could be right or could be wrong. Now, right now, in this instance, it's actually right, so we don't have to beware it. So it's just this. At what temperature about would the ideal gas have of a theoretical volume of 0? Where does it cross the line at 0? Negative 273.15. What is that number? It has to do with the gas laws, doesn't it? Well, here's our hint. Everything must be in Kelvin. That's our conversion factor between Celsius and Kelvin, isn't it? Kelvin is the scale that has the 0 where all molecular motion ceases. That's Kelvin. Okay, so absolute 0, Kelvin, 0 degrees Kelvin, is equal to negative, I left off my negative last period, 273.15. Sometimes chemistry books let you get away with 273 without the 0.15. Okay, so here's a little problem. Let's think about it. If a 1 liter sample of hydrogen gas at 25 degrees Celsius is heated to 75 degrees Celsius at constant pressure, the volume of the gas should increase to 3 liters. True or false? False. She just said false. Why? What does it have to be in? Do we need to go look at the girl on the page again? What does it have to be in? Kelvin. So don't fall into that trap. All problems in this unit for gas laws have to be in Kelvin. So do we agree or disagree? We disagree. Why?
The temperature must be in Kelvin.
Yeah, we'll say temp needs to be in Kelvin. Okay, so they said, well, now do the problem right. Okay, so I got 1 liter divided by 298. That's converting my first temperature Kelvin, equals, we don't know how many liters, X liters, over 348 Kelvin. Cross multiply and solve for X, and volume 2 equals 1.176 liters. Put a box around it. Whoop, whoop. Okay, not too bad. Next gas law is Guy-Lussac. And I would say it's a typo, but it wasn't typing. I wrote it with my own hand. There's a hando, a miswrite. Guy-Lussac says P1 over T1 equals P2 over T2. See, I wrote it wrong. Just in the middle. Started trying to make it into Charles's law. Okay, Joseph Louis Guy-Lussac observed the law of combining volumes in 1808. Based on this law and our knowledge of stoichiometry, we would predict the following results. If you had 2 liters of hydrogen gas reacting with oxygen gas, it'd make 2 liters of water vapor. Where did I get that from? The balanced equation, the stoichiometry. Everybody see that? If I had 3 liters of hydrogen gas reacting with 1 liter of nitrogen, it would make 2 liters of ammonia. So this is some nice math. This is easy math. We can just look at our coefficients. So Amadeo Avogadro interpreted Guy-Lussac's observation by proposing equal volumes of gases at the same temperature and pressure contain the same what? What's Avogadro's law? Avogadro's number, and it is the same what of molecules? The same number of molecules. This is known as Avogadro's hypothesis. So he said, he started figuring out that these gases have the same number of particles in a mole, and that they have the same volume, and that they have the same temperature and pressure. So here we've got 2 balloons. One's got hydrogen, one's got oxygen. Each balloon shown above has the same volume. The gases are at a pressure of 1 atmosphere and a temperature of 0 degrees Celsius. Remember, it has to be at STP. The balloon on the left contains 2.016 grams of hydrogen, and the balloon on the right contains oxygen gas. How many molecules are present in the balloon on the left? Okay, so what do you notice between 2 and hydrogen in the periodic table? What number is that? That is its molar mass. So if that's its molar mass of 1 mole, how many particles are there?
2. Oh, 1, sorry.
What's Avogadro's number?
6.2.
Yes, 6.02 times 10 to the 23rd molecules. You were answering moles. So you see. And how many grams of oxygen are in the balloon? We're pointing to the periodic table. How many grams of oxygen?
32.
Yes, 32. Do y'all understand how he got that? It's the molar mass. What goes with the graham crackers? M&Ms. And what is the volume of each balloon? Do you remember this from honors? It's on our box here. Let's turn the box so y'all can remember. What's the volume? 22.4. It's all coming back to you. 22.4 liters. Okay, that's where we're. Wait a minute. stopped at 5. Why that says 5? Did I leave off 4 on my thing? 3, 5. Well, that's where we're stopping. 6. Huh, these are messed up. I'm gonna have to redo them because there is no page 4. All right, anyway, that's where we're stopping. We'll finish this on Monday because I don't want y'all to get ahead of the other class. Science is great.